what is it asking us to find? The trig functions? Okay, so what are the 6 trig functions? So it's asking us to find these things. Sorry, the bottom one got cut off, but it's not on here. Of beta, right? So we're trying to find it from that angle. So looking at this triangle, are there any that you automatically know? Cosine. Mitchell says cosine. Why cosine, Mitchell?
Since 11.
What do you mean cosine's 11?
Because if you look at our triangle, if you like flip it and put it into a circle, our right angle where it needs to be, and our 13 would be our radius, so then 11 would be our cosine.
Other thoughts on this? Is cosine 11? Wouldn't it be 11 over 13? Why, Campione? So the ratio of the adjacent side to the hypotenuse is 11 over 13. And we can see that. Now, if we think about Mitchell's idea, he's trying to put this triangle in a circle. The problem is cosine and sine are based on what circle? The unit circle. So if I shoved this and made this a triangle in a circle, and I want to make it become the unit circle, what would I have to do to it? Divide it by something. Shrink it is what I heard. Divide it by what? Alice?
Divide it by 13, make the hypotenuse 1.
Right, so that would make the hypotenuse 1. That makes it fit in the unit circle. And there again, we can see exactly why it becomes 11 over 13, because we're shrinking everything down. So we can see that idea as well. Now, are there any others that you automatically know at this point? Brandon? Why do we know secant?
Because secant has an opposite, not opposite ratio, but like the numbers are, it uses the same numbers as cosine.
Secant uses the same numbers as cosine. As a matter of fact, how are secant and cosine related? They're the same, but they're flipped. Say that differently. It's a reciprocal. Absolutely. And if I wanted to write that, like kind of mathematically, how can I show that secant is the reciprocal of cosine?
11 divided by 13 times 1, or 1 times 11 divided by 13.
Is it 1 times 11 divided by 13?
Sorry.
So yeah, so if we do 1 divided by 11 over 13, that really gives us our 1 times 13 over 11. So in other words, what Emily's telling us is that we're really taking 1 and dividing it by the cosine value to get the secant value. Questions on that? So now, if I'm looking for others then, like, do I know any others just by looking at this? Great, so I'm stuck. I've stalled out. I can't go any farther. There's nothing I can find. Jordan?
Could you use the Pythagorean theorem to figure out the other leg?
So Jordan's saying, like, hey, what if we found that leg? Then we'd be able to get other ones as well. So Pythagorean theorem. So we'd have, what would that be? What would that look like? Because that's been screwed up a couple times today, and it's pretty normal that we. What would it look like? Pythagorean theorem. Yeah, go ahead, David.
It's going to eventually be 11 squared times x equals 15 squared.
11 squared what?
Times x.
Y times x.
Because you don't know the other leg.
What is the Pythagorean theorem?
A squared plus b squared equals c squared.
A squared plus b squared equals c squared. So take a look at it again. I've labeled your x for you since you said that was x.
So it's plus x.
Plus
Squared.
x squared equals. Big mistake that a lot of people make is that they just say 11 squared plus 13 squared equals x squared. They don't really thinking about where each of those numbers go. So if we solve this, we end up getting x squared, and I'm going to do all the kind of math just in my head really quick. But 13 squared is 169. 11 squared is 121. So if we're solving for x squared, we end up getting x squared equals 48.
Which is like,
Hey Alice, could you grab that remote there and zoom out for me so you guys can see? There's a little minus sign at the bottom of it. Yeah, a little bit more. And then press the down arrow like there's the, yeah, perfect. Keep going a little bit. All right, awesome. So then if we're solving this, we're going to get x equals the root of 48. Which what? Can be broken up. Now we need to understand something. Is the square root of 48 truly the length of that line? So if I calculate in my calculator, or if I write square root of 48, am I wrong?
no.
No. But Thomas is saying that we're not going to write it that way. We can simplify it. Mathematicians like to see it in a different way. So how would you simplify that?
I divided it by 3 to
You-
get a perfect square.
So you said that 48 is really 3 multiplied by what? 16.
So then you just have your square root of 16 and square root of 3, and then the square root of 16 is 4, so just your 4 square root.
Right. So we're saying like, hey, if we can make a perfect square, we can actually break that out of the square root. So we get the square root of 3 times the square root of 16. I'm running out of room. So really we get x equals 4 roots of 3. So if I come up here and now I label that as 4 roots of 3. Now how does that help us? So, somebody that hasn't talked yet, give me one of the other ones. Give me one of the other values. Robert?
So I just made a connection,
Yeah.
if I'm right, I'm probably.
Go ahead.
But you know how there's like the 3, 4, 5 triangle?
Yes.
Isn't like the shorter leg, if it's 3, the longer leg, if you didn't know it, it's like square root of 3 or something. I don't know, I'm thinking like wrong.
No, it really depends on the triangle, because if you think about it, I could like change all the angles, and so I can change how the sides relate to one another. I can make a really tall, skinny triangle, or I can make a really fat, like short triangle, or I can make like an equally fat, equally tall triangle. So all those ratios will change. It just depends on the angle.
That's right.
Okay. So give me one, Jace. Give me one.
One what?
One of the other values that we need.
I don't know what that was.
It doesn't matter. Look at what we have now. Give me one of the other ones. Sine is what?
The opposite over hypotenuse, so 4 root 3 over 13.
Yeah, opposite over hypotenuse. So 4 roots of 3. My 3 looks janky, but over 13. What's tangent? Michaela?
4 square root of 3 over 11.
What's cosecant? Josh?
Isn't it just the opposite of cosine or sine?
So it's the reciprocal of sine?
Yeah.
Yeah, so it's going to be 13 over 4 roots of 3. And then cotangent is going to be what, Colton?
Well, the reciprocal of tangent.
So it's going to be,
11 over 4 root of 3.
and now we have every single one of these values. Questions? Now, when you're looking at those values, does anybody have anything to add? Yeah, Owen.
Shouldn't we rationalize the denominators?
So what's the point of rationalizing a denominator? What's the point?
You asking?
Yeah.
I guess I don't really know. We're just told we're supposed to do.
Just told you you're supposed to. So let's talk about this. So when we look at cosecant, the value right here, when we're saying rationalize the denominator, what do you mean?
Get the square root or radical out of the denominator.
Get the square root or the radical out of the denominator. Is that value that we have listed right there, is that wrong? No, it's not wrong. It's the correct value. You type it in the calculator and you're going to get the value. You could get an approximation of the value. That is the actual value. But it's just like, let's say the answer to a question was 1/2. And you put 51 over 102. Is that wrong? So why wouldn't we typically list 51 over 102?
It's not simplified.
It's not in simplest form. It's not the form that we prefer so we can easily recognize things. The only purpose of rationalizing is not to make our answer correct, it's just to make it look prettier for mathematicians. So that's the only point. So let's talk about rationalizing though, because some of us might have some trouble with that. So let's say I wanted to rationalize the denominator of 13 over 4 roots of 3. The question becomes, how can we get the root out of the denominator? How can we get the root? So Colton, you kind of were talking about an idea back here. You said we kind of want to do what?
Like, times multiply by itself, like square it.
We kind of want to square it. Because if we, why do you want to square it?
To get the square root out of the denominator.
Squaring cancels out square roots. Does anybody see a problem with this? Think about taking a fraction. And then think about squaring it. We get 1/4. And Bryce just say we get a tiny number. Does squaring it keep the value the same? No. And so that's a problem. Squaring it would would change the value, and we don't really want to do that. So what could we do instead? I like Colton's idea. It's awesome. He's like, I kind of want to square this because that would get rid of a square root. And I think you actually had another idea too.
Yeah,
What'd you say?
just multiply by itself, like square everything. Wow, like, just multiply 13 over 4 of root of 3 by itself.
But if we multiply this all by itself, that would change the value. That's what we just looked at, right?
Yeah.
What do we really want to cancel out? Just the square root. So Bryce, you're saying multiply by what? Square root of 3. So when you look at it, is it kind of like we're squaring that root of 3? It's kind of like it, but why is what we're doing right here, why is that okay? Alice?
Because root 3 over root 3 is equal to 1.
It's multiplying by an ugly 1, but that doesn't change the value. We've multiplied by an ugly looking 1, but it doesn't change the value. Value remains intact. And so when we do that, we would get 13 roots of 3 all over
4, right?
what's root of 3 times root of 3?
3.
3. So we would have 4 times 3,
12.
or 12. That whole process is just how can we make a fraction with a root in the denominator, how can we make that look prettier? It's called rationalizing. It doesn't make the answer any better, it just makes it look better. Okay, it makes it more preferable.